Okay, so let's pick up where we left off yesterday. So we're just about to start this problem. We had just talked about the work energy theorem. So the work energy theorem said that and this is important, the net external force does work on an object, and that is equivalent to the change in the kinetic energy. So we're talking about net external forces. We don't want to use any internal forces to the system, and we need to sum all of the forces to get the change in kinetic energy. In the problems previous to this, we had heard the phrase find the work done by the force applied, or the work done by the force of gravity. And that's fine, but we need, if we're going to try to figure out the change in kinetic energy, we need the net work done. So we need to either sum all the works together or start by finding the net force and then find the work done by the net force, the net external force. And the definition of kinetic energy was the energy due to an object's translative motion, meaning like moving, not rotating. We'll talk about rotation after a break. It's in the units joules. And we had just a little bit of an extra note about what it means to have the velocity vector squared. We know that the kinetic energy is a scalar, so we can actually just add energy. We don't need to add it as a vector or anything like that. Don't have to worry about direction. Okay, so let's look at this problem here. So we've got the space probe DSpace 1 was launched October 24th, 1998, and it's used a type of engine called an ion propulsion drive. The ion propulsion drive generated only a weak force, but could do so for long periods of time using only small amounts of fuel. So the idea is this thing's in space. There isn't any atmosphere to move through, so there's not air resistance. So if we can exert a really, really small force that isn't opposed by anything over a long displacement, we might be able to reach high velocities, have a large change in kinetic energy. So suppose the probe, which has a mass of 474 kilograms, is traveling at an initial speed of 275 meters per second. No forces act on it except for the thrust, which is 5.6 times 10 to the negative second newtons. This external force is directed parallel to the displacement, which has a magnitude of 2.42 times 10 to the ninth. We want to determine the final speed of the probe. Okay, so they've got a nice diagram what's going on here, except they've done their free body diagram incorrectly, right? We know our force has to originate from the center of the object. So let's draw that over. So we're going to have our force of thrust pointing forward, and we're going to have some displacement that starts from here and ends somewhere else. And this is an application of the work energy theorem. So we're going to have that the work done by the net external force is equal to the change in the kinetic energy. In this case, the net force in the x is just equal to the force of thrust, and the net force in the y, or the z if we want to think about 3 dimensions, is just 0. Since this thing's in space, really the only force acting on it is the thrust, like they said. So the net external force is equal to the force from the thrust. So the work done is going to be equal to the force vector times the magnitude of the force vector times the cosine of the angle between that and the displacement times the magnitude of the displacement vector. And that's going to be equal to the kinetic energy final minus the kinetic energy initial. We could plug in some values now and rearrange stuff and solve, but what I'd like to do is manipulate this further so that we can get an expression for the final velocity of the probe, since that's what they asked for. so we're going to write this. We'll just write f cosine theta s equals 1/2 mass v final squared minus 1/2 mass v initial squared. And then we're going to solve for v final. So we'll have f cosine theta s. Let's multiply both sides by 2. I'll get rid of our 1/2 plus mass v initial squared, all divided by mass v final. So there's our expression. That came from the definition of kinetic energy. Kinetic energy is equal to 1/2 mass times velocity squared. Yeah. Yep. Other questions? Okay. All right, so we're going to plug in the information they gave us. What's theta in this case? Yep, the angle between the force and the displacement in this case is 0, so that's 0 degrees. They told us the mass. What was the mass? It's 474 kilograms. And we know the initial velocity was equal to 275 meters per second. We know the force was pretty small. It was 5.6 times 10 to the negative second. And we know the displacement was 2.42 times 10 to the 9th. All right, so let's take a moment to plug all that in and see what it's equal to. All right, so the answer is 805 meters per second. Let's go on to a different question. All right, so in this question, we have a 58 kilogram skier is coasting down a 25-degree slope. They've got a picture here. And near the top of the slope, her speed is 3.6 meters per second. She accelerates down the slope because of the gravitational force, even though a kinetic frictional force of magnitude 71 newtons opposes her. Ignoring air resistance, determine the speed at a point that is displaced 57 meters downhill. Okay, so let's talk about this a little bit. If we weren't in the work energy section, how would you guys do this problem? We did like inclined plane stuff before, right? So like how were we doing this before? We would like rotate the coordinate system, and then what would we do? Yeah, we'd need to find the net force along the incline, and that would help us solve for the acceleration, and then we could use the kinematics equations to solve. But what we saw the other day was that the work energy theorem is actually directly related to that one kinematics equation. So the technique that we're using here is actually the same. It's a different conceptual idea, but mathematically the algebra all ends up coming out the same. So we try to keep that in mind. But so basically we've got a person starting with a certain initial energy. The net external force on them is going to do some work over a displacement S, and that's going to cause their kinetic energy to increase. So we just need to figure out what that net external force is first. And we're used to doing this in inclined plane problems. So we've got, I'm just going to draw a box, got our person, and they told us that we've got the force pulling her down the incline is just the force of gravity, and we have a kinetic frictional force that's opposing her motion that's 71 newtons. So we know that we have a kinetic frictional force that's pointed up the incline, and we've got some component of her force of gravity pointed down the incline. And if we rotate the coordinate system so that x lies along the incline, then we call that the force of gravity in the x. We'd have the force of gravity in the y as well. But just as a really quick note, remember that if we're answering a free response or multiple choice question and they ask us to draw the forces acting on the object, so draw a free body diagram, they give us a little dot, we're supposed to just use the vectors they provided. So in this case, we would draw the force of friction and the weight, and we would leave it like that. After that, we could draw the diagram with the weight decomposed along our rotated axis. Okay, but we would start with the diagram on the right. Okay, so we need to find the net force in the x, or along the incline. Let's call, I actually want to call down the incline positive, so I'm going to switch what I drew here. So I'll have this be positive. So we'll have the force of gravity in the x minus the force of friction. That's going to be equal to our mass times acceleration. If we were going to do this with kinematics, like we were talking about, we'd solve for acceleration. And what's the expression for the component of the force that's along the incline? Do you guys remember? Yeah, it's mg sine theta. When we have these inclined plane problems where we rotate the coordinate system, we had proved previously that the component along the incline was dependent on sine theta. So we have mg sine theta minus the force of friction. That's our net force. That's what we want to use when we're calculating the work. That's our net external force. If we were looking at the incline, actually we left out a force here, didn't we? We had the normal force. We should have put the normal force here. So the net force in the y is 0. So we can take that and say that the work done is going to be equal to the change in kinetic energy. The work is going to be mass, gravity, sine theta minus the frictional force times our displacement s. In this case, what's the angle between the displacement and our net external force? Zero. Yeah, because we did this work like we do on inclined plane problems, we made sure that we found the net force along the incline, right? And the incline is the direction of displacement. So we've already actually taken care of that part. So we've got a cosine 0 there. And then we've got our displacement. That's going to be equal to our change in kinetic energy, which